From self-driving cars to training powerful large language models, reinforcement learning is transforming our world. I have become fascinated by this field. In this video, I will show you how we can apply a popular RL technique, Deep Q network or DQN, to a classic control problem, swinging up and balancing an inverted pendulum. Some of you might say, why not just use something like a PID control? I know that PID might be a better solution in this case, but the point is not to create a perfect control system to balance a pendulum. The goal is to learn together the end-to-end process of applying reinforcement learning to a real problem. So we will tackle this challenge in three progressively harder environments. First, we will train our agent in a simple simulated environment called Gymnasium. Then we will move to a realistic PyBullet simulation and add real-world physics to our environment with factors like motor torque and friction. Finally, the exciting part, we will deploy our trained agent to control a real physical inverted pendulum. I will show you how an agent trained mostly in simulation performs in the real world, including the challenges and successes. While there was a slight performance drop from simulation to reality, the agent still performed remarkably well. I will cover the basic concepts, theory and code. This is going to be a long one, but hopefully you will find the world of RL as fascinating as I do. Let's get started. The learning process at the core of RL is very similar to the human learning process. As kids, we got rewarded by our parents or teachers for doing good things. That encouraged us to do those things more. We got reprimanded for doing bad things. If you are an Indian like me, the reprimanding was occasionally accompanied by significant negative reinforcement called ass whooping. But I digress. This negative reinforcement discouraged us from doing the bad things, and that is how we learned what to do and what not to do. RL learning process is very similar to this, where we have an agent that interacts with an environment. The agent takes actions based on the state it is in. Depending on the action taken by the agent, the environment gives the agent a reward and puts the agent in a different state. The entire goal here is to teach the agent which actions to take in which states so that the overall reward it gets, called the return, is maximized. For that, we will use an algorithm called Deep Q Learning or DQN. We will get to DQN in a bit. Before that, let's get to know the first environment we are going to deal with. It is a simulated simple environment called Gymnasium in which we have an inverted pendulum on a cart. The cart can move left or right. These are the two possible actions our agent can take. So this becomes our action space. The objective for our agent is to keep the pendulum vertical. The information we get about the pendulum at each time step is we get the position of the cart, the speed of the cart, the angle the pendulum is making with the vertical, and the speed of rotation of the pendulum. This becomes our state space we are given at any time step. Based on this information, our RL agent has to decide whether to move the cart to the left or to the right to keep the pendulum vertical. The episode ends if the pendulum falls beyond plus or minus 12 degrees or if the cart goes out of bounds beyond plus or minus 2.4. The episode is truncated if the number of time step exceeds 500. For every time step the pendulum stays upright, that is, it doesn't fall beyond plus or minus 12 degrees and the cart remains within the bounds, we give a reward of 1. If it falls beyond plus or minus 12 degrees or if the cart goes out of bounds, we give a reward of 0 and the episode ends. Our goal is to maximize the total reward earned during an entire episode. Let's take a look at some code to see how we can interact with this environment. For that, we are going to head over to Google Colab just so that it is easier to run and see each time step. Let's first import Gymnasium and then create our environment using this gymnasium.make method. The environment we want is cartpole v1 and the render mode is RGB array, which allows us to see each time step. We have to reset the environment first, which gives us the initial state of the environment. And then when we render it, we get a graphical representation of the pendulum and the cart. Now, if we want to take an action in this state, let's say we want to move right. We would do that using the step function and passing it the integer 1. Remember, 0 is for left, 1 is for right. Let me do this several times so that the effect is apparent. Now we can see the cart has moved to the right, which has made the pendulum swing to the left. Now that we have understood our environment and know how to interact with it, we can turn our attention to the Deep Q network DQN algorithm we are going to use to train the agent to balance the inverted pendulum. This can sound complicated, but it really isn't. So please stick with me here. It will be totally worth it when all of this comes together at the end. First, let's just focus on the Q part of this acronym. This Q stands for action value function. The name action value function itself is very suggestive. It provides us the value of taking an action in a particular state. At time t, if we are in state S and we take action A, the action value function represents what is the return we can expect. This is how we say it. Expected return GT given ST and action AT. Notice I'm not saying reward here. I'm saying return, which is the sum of discounted rewards during the entire episode. Imagine an episode like this. We are in state ST at time step T. We take action AT and get a reward RT plus 1. This puts us in state ST plus 1 where we take action AT plus 1. We get reward RT plus 1 which puts us in state ST plus 3, so on and so forth. Then we can write GT, the expected return, as RT plus 1 plus gamma times RT plus 2 plus gamma square times RT plus 3 and so on. Gamma here is the discount factor. It is typically a value less than 1, something like 0.98 or 0.99. Why are we multiplying by gamma for each successive reward? So that we value immediate rewards more and the rewards that we get in the future less. We are impatient and we want to get to higher returns faster. Gamma helps with that. Now this then becomes GT is equal to RT plus 1 plus gamma times GT plus 1. Imagine a scenario where we know the expected value of the return for all possible actions. We can then choose an action that maximizes the return to get the best result. But we may not want to always do that. If we want to explore the state space a bit more to see if there are any other states that can potentially yield us larger returns that haven't been explored yet, we might every now and then want to take a random action. And which action we choose, whether we choose a maximizing action or whether we choose an exploratory action, is governed by the policy which is represented by this term pi that I sneakily added earlier. A policy that always takes an action that gives highest expected return is called a greedy policy. Another type of policy that allows for exploration is called an epsilon greedy policy. It takes the maximizing action with a probability of 1 minus epsilon, but takes a random exploratory action with a probability of epsilon. This will come up again when we look at the code. Now let's take a look at how the return is calculated in the Q-learning algorithm. In Q-learning, regardless of the policy we are following, while calculating the returns, we assume that we will choose the action with the highest action value. So then the above equation becomes GT is equal to RT plus 1 plus gamma times max A QST plus 1 AT plus 1. This term represents the choice of highest action value in the next state. This equation here, where we use a maximizing action to calculate the return without taking the policy into account, makes Q-learning an off-policy algorithm. If we put that in this equation, QSTAT then becomes expected value of RT plus 1 plus gamma times max A QST plus 1 AT plus 1 given we are in state ST and take action AT. How do we get this expected value? We learn it. We start with a random action value function. Then in any particular state, we take an action based on the action value function and the policy. Observe the reward and then adjust our action value function based on the observed reward. The equation that is at the heart of all of this looks like this. So in state ST, we take action AT, we observe the reward RT plus 1 and go to state ST plus 1. The observed return or the target is RT plus 1 plus gamma times max A QST plus 1 AT plus 1. QST AT is our existing estimate. The difference between the existing and the learned return becomes the error. How much we adjust our current estimate of the action value is governed by alpha, the learning rate. At every step, we nudge our action value towards the observed value. We do that enough number of times and we can learn what the actual action value function is. Now, all of this works in cases where the state space is finite, where we can create almost like a table that contains states, possible actions in each state, and the associated value of each action in each state. If the state space is too large or infinite, as we have in our case of inverted pendulum problem, using conventional Q-learning becomes very tricky. In our case, as an example, the angle of the pendulum can be any fractional value between plus or minus 12 degrees, making the state space infinite. There are hacky ways to get around this, like discretizing, but it is very tricky to make them work. So what do we do? That is when the deep network part of the DQN acronym comes to our rescue. Deep neural networks are very good function approximators. We can use them to give us the action value even if the state space is continuous or infinite. This is our current state with conventional Q learning. We query our Q table to know the value of a state action pair. Instead, we can give our Q neural network a state and get the action values for all the possible actions, and then we can choose the action based on the action value. For that though, we will have to change our previous equations a bit. Error then gets modified to this equation. Theta here represents the weights of our neural network, completely different from the variable we are using to represent the angle of the pendulum. Which should be very apparent from the context. From this, we can calculate mean squared error or any other type of loss and then train our neural network to minimize the loss. In our case, we will just use the mean squared error to calculate the loss. Now, if we run a backward pass through our neural network, we should be able to calculate the gradients, and our chosen optimizer can update the weights of our neural network based on the learning rate alpha. If you're still with me, we have cleared a major hurdle. We have the loss that should be minimized to train our neural network. But we still haven't talked about how we feed data to the neural network to train it. Here is one way we might try to do it. At each time step, we can use our neural network to get action values. We can choose an action from this based on our policy, observe the reward and the next state we land into. Use our neural network again to get QST plus 1, AT plus 1 theta, plug it in the formula to get the error and then the loss. We can then backpropagate to get the gradients and calculate the new weights. What's wrong with that? Unfortunately, using a neural network comes with its own set of issues. The first one being that the data being fed to a neural network should be IID. That is, it should be independent and identically distributed. But our data generated from sequential time steps in an episode is not independent at all. The next state depends on the previous state. To solve this, we use what is called a replay buffer, a snapshot of each time step called an experience that includes the state at time step t, the action taken in the state, the reward received, and the next state is stored in the replay buffer memory. And when we need data to train the network after each time step, we just randomly pick a data point from the replay buffer and use it. In practice though, we apply the same method of using a replay buffer but with a slight twist. We don't just pick one data point. We randomly pick several data points from the replay buffer, create a batch of data and use that for the learning step. We do this at every time step and slowly the agent magically learns to predict the action values in each state. Once you know which action will provide how much value in each state, you can choose them accordingly to maximize the returns. There is one last thing we need to understand before we start coding. If we use just one neural network to calculate the estimate of our current action values and the targets, both, our neural network will change at every step when we update the weights. So essentially, we will always be trying to catch a moving target. This makes it almost impossible for our neural network to learn stably, and it increases the risk of divergence. The way we deal with this problem is that instead of having one network, we use two networks. One is what we call an online network, and the other one is what we will call a target network. We will update the online network at every time step, but we will use the target network to calculate our target values. Every few time steps, we will make our target network weights and parameters equal to our online network weights and parameters. This will significantly help our neural networks to learn without divergence. The error then gets modified to this equation. After that very long explanation, we are ready to look at the code. We start by importing Gymnasium, our simulation environment. Then we import PyTorch and its associated modules that will allow us to create and train neural networks. I'm using PyTorch, but something like TensorFlow can be used too. Then we import NumPy for arrays and Matplotlib for plotting the data. Next in the code, we have a class called FCQ. This is where we define our neural network. In our case, it is a fully connected neural network with linear layers. While creating an object of this neural network class, we can specify the input dimensions, output dimensions, and the size and the number of the hidden layers. In our case, the input dimension is going to be 4 because we provide 4 values to the neural network: the position of the cart, the velocity of the cart, the position of the pendulum, and the velocity of the pendulum. The output dimension is the number of possible actions. That is 2 for us, left or right. If we have a GPU available, we can use it. If not, we can stick to using the CPU. Now, if we scroll down to our main function, I have created 2 instances of this class. One for the online network and the other for the target network. I'm calling them online model and target model. env.observationspace.shape0 gives us the number of variables being used to define the state of our environment. 4 in our case, as I said. And env.actionspace.n gives the number of possible actions, 2 in our case. The tuple 16,16 gives us the size and the number of our hidden layers. So we have 2 hidden layers with 16 nodes each. Back to the class, if we pass a tensor containing the state values to this forward function, we will get an output with the action values for each of the actions. So the output of the forward function will be a 1 by 2 tensor containing the action values of the left and the right actions. The next class we have in our code is the replay buffer class. This allows us to create a replay buffer which stores our experiences. After every time step, we call the store method of this class, which stores the experience that contains the state, action, reward, the next state, and whether the state was terminal or not. All of this gets stored in a collection of NumPy arrays. The index gets incremented by 1 after an experience is stored. The size variable allows us to keep a track of the number of experiences that have been currently stored in the buffer. When the buffer gets full, it starts back again at the index 1 and starts overwriting the older experiences. To draw random experiences from our replay buffer, we use this draw samples method. The next class is our DQN reinforcement learning agent class. When we create an instance of this class, we pass it our environment, an instance of our replay buffer, our online model, target model, the optimizer we will use to train our neural network, warm-up batches, update frequency, epochs, and our gamma value. I will explain a few of the variables I've used here. Warm-up batches is the number of batches we want to collect after which we want to start the training. This makes sure that we have enough experiences to sample from during the initial phase before we even start the training. The update frequency is the number of time steps for which we will keep the target network constant. The epochs is the number of times we want to run the training step, which is irrelevant in this specific case because we will deal with it in our next environment. The next 2 methods we have in our DQN class are the choose action eGreedy and the choose action greedy methods. They allow us to choose an action in an epsilon greedy manner and in a greedy manner. As explained before, the epsilon greedy method allows us to choose a random action every once in a while so that we can explore the state space to see if we can find states that might give us higher rewards. The choose greedy action method always gives us the action with the highest action value. Moving on, we have the interaction step method. We pass a state to this method. It will use an epsilon greedy action, pass it to the environment and get the next state, reward, terminated flag, and truncated flag. It will create an experience tuple and store it in the replay buffer. The next method is where all the learning happens. We draw the samples for learning from the replay buffer and convert them to tensors. We then use our target model to calculate the max AQ plus 1 AT plus 1 theta value in this formula. We don't want to backpropagate through our target network. So we use this detach here. Target gets calculated using this formula here. The 1 minus terminals makes sure that we do not use the terminal experiences to calculate the QST plus 1 AT plus 1 theta values, because if the experience was terminal, there should be no next state. Then we use our online model to calculate our QSTAT theta value. We calculate the error between these values and then the loss, which is the mean squared error in this case. We zero the gradients and then backprop, which updates the weights. The The final method in this class is the soft update weights method. This makes the target and online model's weights and parameters the same after every few time steps. Now let's see how all of this comes together. We first create all the instances of our classes and create empty arrays for variables we want to store and plot. Then we start running our episodes. In the initial period of our training, we want our agent to explore more and then gradually as it learns, we want it to take more and more actions with higher action values. For that, we simply decay our epsilon. We start with a high value, which means our agent is prone to taking random actions a lot more in the earlier stages. And gradually, as we decrease the epsilon value, the agent takes more and more optimum actions. For each time step, we get the reward and add it to our episode score variable, which keeps a track of episode scores. Then we use the agent.learn method described earlier to train our online model. Every few time steps, we make our online model equal to our target model. If the pendulum falls or if the episode reaches maximum steps, we end the episode by exiting the inner for loop. Finally, we record a few values for plotting and then plot the variables. When I run this code, we can see a few things here. First, the epsilon value decreases as expected, and slowly the episode scores start to go up, which indicates that our agent is learning. After 600 episodes, this is what the graph for the episode score and the moving average of episode score looks like. You can see that the agent has learned to keep the pendulum vertical for more number of time steps. When our learned agent tries to balance a pendulum, this is what it looks like. The entire code for everything I've talked about so far and everything I'm about to explain is in the GitHub repo. The link is in the description below. I have put a lot of comments in the code to explain it. Feel free to check it and play with it. Now that we know our algorithm works for a simple environment, we take things up a notch and try to make it work for a more complicated simulation environment that is closer to a real-life system. For that, I designed a setup which consists of a DC motor. We control the DC motor with this motor controller, which can give it a positive or a negative voltage, making it move in clockwise or anti-clockwise directions. The motor is connected to an output shaft through a belt. The output shaft makes the carriage rotate, which in turn swings the inverted pendulum. The angular position of the carriage and the pendulum is measured by these two AS5600 magnetic encoders. We can calculate the velocities of the carriage and the pendulum using the positions in successive time steps. All of this is connected to a Jetson Orin Nano that receives the I2C signal from the AS5600 encoders, performs the computations, and commands the motor to move in clockwise or anti-clockwise direction. Our state at each time step looks like this. S is equal to phi dot, theta, theta dot. Phi can be between negative 3.14 and positive 3.14. We don't want the carriage to move past these because then the wires will get tangled. Phi dot is the velocity of the carriage. Theta is the angle the pendulum makes with the vertical. It is 0 at the top and goes all the way up to 2 pi on the other side. And of course, theta dot is the velocity of the pendulum. In our previous environment, the pendulum conveniently started in an upright position. In our new environment, the pendulum starts in its lowest position. So our agent needs to learn how to swing up the pendulum first and then balance it. For this, we will change our reward function a bit. This is what the new reward function looks like. Reward is equal to cos theta minus 0.002 times theta dot square plus 0.001 times cos phi. With this reward function, when the pendulum is in its upright position, that is theta is 0 or 2 pi, we get a maximum value of 1 for this term. So we are giving a high reward if the pendulum is in an upright position. It gets a negative reward automatically because of the cos function when it is in the downward position. That is, theta is close to pi. But at the same time, we want the pendulum to not sling around. We want its velocity to be as low as possible in the upright position to keep it stable. So we are punishing the agent slightly if the pendulum has any velocity. And lastly, we want to encourage the agent to keep the carriage in a phi equal to 0 position. So we give it a slight reward when the carriage angle is close to 0. I modeled this setup in SolidWorks and created a URDF file which takes all the kinematics of the system into account. It contains information about the joints in the system, the links that the joints are connecting, and any other associated information about the links and the joints. This URDF file is used to import our system into PyBullet, which is our simulated environment. To mimic the real world, I had to calculate the friction in the pendulum joint so that I could use it as one of the parameters in PyBullet when modeling the system. For that, I dropped the pendulum from a 90-degree position. I recorded the video and measured how far the pendulum swings to the other side. In a frictionless world, the pendulum should have swung all the way up to 90 degrees on the other side. In the real world, the friction in the bearings prevents it from doing that. Then I can use this formula to calculate the frictional torque on the pendulum and use it in the simulation. The value I got for friction using this method was about 0.0047 Newton meters. The other parameter was the torque applied by the motor. I could just use the specification provided by the manufacturer for this, 0.03 Newton meter in this case. All of this is good, but there is a problem. Imagine a scenario where we use the exact same method as we did in our previous environment to make our agent learn. At every time step, we do a forward pass, store an experience in the replay buffer, gather a batch from the replay buffer, and then backpropagate through the neural network to adjust the weights. The problem here is that the time required to do a forward pass and a backward pass is way too long. By the time we have completed the passes, our agent will have already moved to a different state. If the time delay is small, the neural network will learn to account for it, but very long time delays can be problematic. In many cases, by the time we have taken an action, the pendulum might have already fallen to a non-recoverable position because of the delay. To get around this problem, we can run an entire episode, and when the episode ends, we do the learning step. During the episode, we only do forward passes to get the action values. Since we aren't doing backward passes at every time step, this allows us to save time and make the system more responsive. At the end of the episode, we make up for the reduced frequency of learning by running the learning step multiple times. This is how we do it in the code. We do it by executing the learning method here after the terminal or truncated flag is found to be true, and we use a for loop to execute it multiple times. Since we are now creating our own environment, we need a new method to reset our inverted pendulum after every episode. We use this reset joint swing up method for that. It randomizes the initial angles of the carriage and the inverted pendulum and sets the friction in the pendulum joint. GetState method provides us the current state of the system, and sendAction makes the motor move in one direction or the other. In the main loop, the initialization of our class objects and our variables should look the same compared to the code we used for our earlier Gymnasium environment. Next, we set up the PyBullet environment and get into our for loop and the episodes. All of this is the same as the previous code. When we run this code, we can see the agent starts its learning process. It runs an episode, takes action, and gathers the reward at each time step. The experience gets stored in the replay buffer. When the episode ends, we draw a batch of experiences from the replay buffer and adjust the weights of our online model. After we have let this run for 8,000 episodes, we get this graph of episode returns. There is this initial period where the return graph oscillates. The agent during these episodes learns to crash itself. That is, it moves the carriage to the max 5 position where it gets a reward of minus 100 and the episode ends. The overall episode reward with this strategy is still higher than if the agent continues the episode and keeps struggling to find a higher reward. It will get a higher reward only if it swings the pendulum up, but it hasn't figured that out yet. So crashing itself quickly ends up becoming a decent strategy that allows it to achieve a local maximum. Fortunately for us, the agent finds a way out of the local maximum and figures out how to swing the pendulum up. After about 3500 episodes, we see the return values start ticking up. This is the point where the agent figures out that it can get a higher return when it tries to swing the pendulum up. It keeps learning how to keep the pendulum in a vertical position for a longer period of time until it reaches a value of 300 or so, where it learns to swing up the pendulum and then balance it stably. Let's observe the pendulum at different stages of its learning process. At episode 2000, the agent finds a local maximum strategy of crashing and ending the episode. At episode 4000, the agent has figured out it can get higher reward if it swings the pendulum up, but it is still moving too fast to be stable. At episode 6000, it has learned to swing up the pendulum and balance it. At episode 8000, it is now able to do that quickly in optimum number of steps. We now have an agent that can swing up a pendulum and balance it in a real-time physics-based simulated environment. This is beautiful. Now comes the more exciting part, translating this to the real world. For that, we are going to have to use multi-threading. I'm going to create a thread which I'm calling the measurement thread that collects the data from the magnetic encoders to get the angles of the carriage and the pendulum. It also calculates the velocities of both the joints. We can get the state of the system as and when we need by just looking up the state variable. By doing this, we can use some of the downtime in our main thread for getting the angles and calculating the velocities, which is a continuous ongoing process when the code is running that keeps happening in the background. The main thread runs the forward passes and sends the action to the motors over I2C to make them move. That is it. Remember that we are directly deploying our model that has learned in simulation to a real world environment without any additional training. Here are some of the runs that I recorded. As you can see, the episode return is, well, it's positive and in the range of 50 to 100. That is actually great. If you remember, it took the agent more than 4000 episodes to get a positive score in PyBullet simulation. Here we can skip all of that and use our learnings from simulation and apply them directly to the real world. Now we can further train the model in real world and make its performance as good as what we saw in the simulation. But that was not the goal of the video. The goal was to learn together the end-to-end process of applying reinforcement learning to a real-world problem, starting with simulation and translating it to the real world. And I think we have done enough here to demonstrate that process. I hope you enjoyed the video and were able to learn with me. Let me know your thoughts in the comments. The entire code is on GitHub along with a written article that you can go through for a few more details. Subscribe for more such content. Thank you for watching.